Okay, so first I wanted to thank the organizers, so Kai, Harris, and Asterios for inviting me to do this. So I wanted to say, first of all, that like when Kai asked me to do this, I was actually pretty surprised because, like I said, I I don't really know anything about psychoacoustics or timbre, but what I do know about is synthesis, I guess, and working with musicians and thinking about timbre from a more practical standpoint. And he said, yeah, sure, just show us what you do. And I think that's what I'll try to do today, is to try to show you how like concepts of timbre like intervene when you're trying to design tools for musicians and how musicians think about it. But actually, like the real thing I want to do today is to almost talk about or show you something which is nonverbal, because I just really want to play a lot of sounds for you so you can get an idea of what the timbre space is currently, like when you're using synthesis tools. Okay, so to that end, and also to do kind of a sound check, let me play some sounds here. And if you just let me know how the levels are.
I don't hear anything.
Nope. Okay, hold on. I think I forgot to share audio hold on. Let me just do this one more time. Okay. And yeah, I have to share computer sound. That's right. Okay, let me try one more time. Did that come through?
Perfect.
Great. Okay. So I'll play all three again. So that was the first sound. Okay, so those sounds were intended as emulations, first of a guitar-like instrument, a brass instrument, and something resembling a gong. And they're all synthetic. And by synthetic, I mean that there was no audio used to drive these emulations. And there was no audio used for analysis purposes either, to come up with parameters to use to drive the synthesis. So they were all based on very small codes that took in, on the order of about 20 to 30 numbers apiece. And, one thing we're really going for here in the group is to try to do emulations that capture some of the natural qualities of acoustically produced sound. And let me just put up on screen here a well-known old quotation from John Chowning from his Audio Engineering Society journal paper from 1973. And I'll just read it out. So he says, of interest in both acoustical research and electronic music is the synthesis of natural sound. For the researcher, it is the ultimate test of acoustical theory, while for the composer of electronic music, it is an extraordinarily rich point of departure in the domain of timbre or tone quality. The synthesis of natural sounds has been elusive. However, recent research in computer analysis and synthesis of some tones of musical instruments has yielded an insight which may perhaps prove to have general relevance in all natural sounds. And it's hard for me to think of a quotation that I agree with more than that. And there are a few things I just want to point out about it, like looking back on it now, 47 years later. I mean, one is his use of the word natural. So this comes up a lot. And I find this really interesting because I would have thought that, at the time, like in 1973, when all these new tools were appearing, that John Chowning would have been happy enough just to have some fantastic, interesting new sounds. But that wasn't really enough for him. And you get the sense that there's almost a little bit of disappointment on his part that computers aren't able to produce sounds like those in the natural world. And he says, in fact, that natural sound production has been elusive. And I think at this point, 47 years later, we can say that it's not really elusive anymore, it's just difficult. So it can be done, maybe in another 47 years, it'll be standard or easy or something, but at the moment you can sort of get closer to some of the sounds that are produced by, like acoustically. But John Chowning was using mainly FM synthesis at the time. And if you want to approach natural sound production, a good way to do it is to make use of a physical model. So this leads into the main body of the talk here. So physical modeling synthesis, it's an approach to synthesis which goes back a long way. It goes back, in fact, further than John Chowning's work, to early work at Bell Labs by Kelly and Lochbaum, who did vocal synthesis. But the first really like musical instrument model was due to Pierre Ruiz, who was a master's student at Urbana-Champaign in 1969, 1970. And it's best to think about these kind of methods like in contrast with standard synthesis techniques that are maybe like sometimes referred to as abstract or can be thought of as perceptually motivated. So things like additive synthesis or FM or granular, where, I mean, the kinds of parameters you're supplying to the synthesis algorithm are perceptual. They're like frequencies or something. Whereas here, the ultimate arbiter of the sound is a system of differential equations. And there are a lot of different ways to do this, and they're not all the same. They differ quite a lot in terms of efficiency, for one thing, but also how general they are, like what types of systems that they can capture. And this has actually a big impact on the resulting timbre, like space that they can span. So one way of doing it is something called modal synthesis. Here, you take your system, whatever it is, it could be a string, and decompose the vibration into modes, each of which oscillates at its own natural frequency. And then in order to generate a sound, what you then do is take some weighted combination of those modes. So it's a bit like a physical version of additive synthesis. And this was pioneered at IRCAM, and it forms the basis for something called Modalise, which is a very popular synthesis system. And it's based on really the hypothesis of linearity for over the expanse of the thing that you're trying to model. So that's what allows you to have this independent behavior of all the different modes. So it works well for systems which are described as linear, like say, like a bell or something. That's a great example. But for nonlinear systems, it doesn't apply so well. And then there are waveguides, which is a different approach. And here, you decompose the vibration of a system generally described in 1D, so something like a string or an acoustic tube, into waves, which, provided that they travel at a constant speed and don't interact with one another, like while they propagate, then there's an efficient representation that really was kind of the genius moment of Julius Smith at Stanford, was to realize that that you could represent these using delay lines and pretty much avoid any kind of arithmetic calculations. So this is really one of the two great ideas in synthesis, the other being FM. But it's great mainly because it's so targeted. Like it works really well for strings and for acoustic tubes, but it doesn't extend to other types of systems. And then there's kind of the brute force approach. So if you were like a mechanical engineer or something and knew nothing about musical instrument modeling, probably the first thing you do is just try to represent your system over a grid and develop a recursion that computes the solution or an approximation to it numerically and updates at the audio sample rate. And this is like an expensive way to proceed. I mean, a lot more expensive than something like a waveguide. So for a string, for example, trying to operate this way might be like 100 to 200 times more costly in terms of compute. But it's more general because we're not assuming anything about the solution. So we're not assuming that there are modes there, that we're not assuming there are traveling waves. We're just naively computing a solution. And what this means is that the space of timbres that you can reach is wider. Okay, so let me say a little bit about what we did for the last little while. So what we wanted to do during something called the NEST project, which was really try to see how far we could go in terms of exploring timbral possibilities of physical models. And there were really three stages to the work. So one was algorithm design. And there were a bunch of us working on this. Each of us had a target system that we worked with, like say the symbol. And then you come up with a mathematical model for it, and then design sound producing prototype code, usually in MATLAB. And this is where, interestingly, this is where timbral considerations really came into play in the choice of the mathematical model, because, you know, you might think that, you know, once you have a model for something, just write some code and turn the crank and then your sound will come out. But actually, like for any given system, there may be hundreds of models, and they all differ in terms of levels of approximation, the kind of things they model. Some of them model things that you can't hear, so they're probably inefficient. Some of them don't model things that you can hear, so they're not sufficient for the purposes of synthesis. So you have to be really careful and think a lot about like perceptually about what all the terms in these differential equations do. And I'll do an example of this in a little bit. The next part of the work was hardware acceleration. So we worked with a team that ported all of our codes from MATLAB eventually into CUDA so they could run on a GPU server. And then we invited over a lot of musicians to work with them directly. So this was really a lot of fun, kind of like grindingly difficult at sometimes, but fun nonetheless. So we brought them over, did workshops with them, showed them how to use the systems, and ended up with about 10 or 12 multi-channel compositions. And I'll play you an excerpt from one of them towards the end of the talk if there's time. Okay, so what I'd like to do now is just like briefly go through like some of the systems that you can approach this way. And I'll start with the one that's probably conceptually easiest to understand, so brass instruments. So here, you're always working with an acoustic tube model. And the tube is generally of a variable cross-section, and the cross-section of the tube has a big impact on the resulting timbre. But you know, in our project, we wanted to really try to model some of the more nuanced, delicate effects, timbral effects actually you get when playing. So we also introduced valve models as well. So it allows for things like half valving and stuff like that. So I'll just take you through the kind of sounds you get, and like invariably, like when you start playing with one of these things, like the first sound you get out will be something like this. Which, you know, like to some musicians, it's like amazing. There's all this kind of interesting stuff going on. Some people think it's like horrible. You know, it sounds like, I don't know, your 8-year-old kid, like learning how to play a trumpet or something. But anyway, so as you learn like how the parameters work, it's a bit like learning a real instrument. You learn how to kind of stabilize the sounds a bit. And then you can start to explore standard gestures. And then usually at this point, like the composers kind of get bored with that because they figure, I mean, they can do that with an ordinary trumpet. So they go off and try to do really strange things with it, like this. So that's basically a really long brass instrument. I think it was 20 meters long or something. And you know what happens when you sort of depart from like more physical, like geometrical constraints is you start to go back into territory where the sound starts to be more synthetic again. So anyway, so let me move on to stringed instruments. So we did the same kind of thing with stringed instruments like the guitar in particular. And we tried to sort of move away from the model of, say, changing pitch on a guitar string by thinking about just changing the length of the string, which is a kind of a, you know, a rough approximation to what's happening, but you lose a lot of the really interesting like timbral effects that way. Because, you know, when you put your finger down on one of the frets, I mean, it really matters like how hard you push and, you know, whether you actually hit the fret or not. And this has like a really big impact, in fact, on like it's a sort of an accumulation of all these micro effects that you get that changes the timbre. So I'll just play you a few sounds here. So here's kind of a standard strum guitar sound. But here's like a sort of a bar chord slide. And there, like you hear kind of as the fingers like pass over all the frets, you hear like little bits of noise there, which are due to rattling. Like if you have an imperfect kind of trapping of the string against the fret, it'll rattle a bit. You get this kind of noise there, just like you do in a real instrument. And then you can also sort of play on the harmonics too by adjusting the forces that you're applying. Okay, so, you know, if it's like if it's realism and natural sound that we're going for, then you really need to consider the full room too. So we spent a lot of time on something which, which isn't strictly musical acoustics, it's more room acoustics, trying to do simulations of big rooms. And although I guess, like from the keynote this morning, I guess I've learned that that's not really considered to be part of the timbre. So anything that's room reverberation is, I guess, excluded. But certainly, like composers use this a lot, like in the same way that you would use reverb normally, just to try to enliven their sounds. And so you can place these sounds within, or these instruments within rooms now. So here's the same trumpet sound now within the Musikverein in Vienna. And 3D modeling also plays a big role in, particularly in percussion instruments. So things like the timpani drum or the snare drum, where you have some cavity there, which really will affect the timbre of the sound a lot. So because it'll possess its own modes. So here's a timpani sound. The snare drum. A set of gongs actually all together in one acoustic space. And where the timbre space really starts to get big is when you start providing environments for musicians to build their own instruments. And this kind of, I guess, answers the question that Kai had right at the beginning of the talk here about the prepared piano. Well, here's the model, actually. So it's a bunch of stiff string models, but where there are sort of configurable connections which allow for contact or communication between the various strings, either through rattling or stiffness or what have you. And this, amazingly, is real time these days. So I'll just play you like a couple of videos of the plugin that we're sort of working on right now. So this is the beta version. And like what you hear is like a really huge timbral variety. So this is like a 25 string setup, just being played with one set of notes. But then if you listen to the tail, what you hear is a kind of a lot of timbral variation happening over a long period. There are all sorts of questions about technique and performance that arise when you look at these, when you start playing with these things, because you realize that, even changing the times at which you strike these notes by a couple of milliseconds on either side will lead to a like some kind of divergence in what the tail is for these sounds. So like we're not sure like how people are going to learn how to play these things in practice. And here's another more extreme example. So this is where you're sort of modifying the connections like in real time. Okay, so that's actually the same instrument as the previous one, but under a different set of parameter choices. Okay, so let me move on now just to talk a little bit about mathematical models and how you can sort of think about trying to link some of the parameters you see there with timbre. Okay, so one really important way to think about building these kind of models is in terms of layers. So like it's always the case like that for any physical model, it's sort of built like a bunch of Russian dolls or something. Like, so at the very middle, there's something really simple. And then you add on layers to it, which correspond actually to terms in some differential equation. And each one adds something new to the eventual timbre. Here's an example. So let's take the case of the snare drum. So if you just listen to the sound of a membrane in isolation, like here's the kind of sound you get out. So, you know, I mean, you might consider that to be a drum. I don't think I would. It sounds very synthetic. It's sort of pitched. You can hear the, you know, the modal frequencies of the membrane there, but that's about it. So for a snare drum, though, the thing that really determines the character of the sound is the snares, of course. So these wires that are in intermittent contact with the membrane. And what happens is, because of this intermittent contact, and because like there's a kind of decoherence over time, you end up with noisy timbres. And then finally, though, like looking at a real snare drum, there's more to it, of course. Like in fact, what you really have is a mallet striking one membrane, which sets like the acoustic field inside an instrument into motion, which sets another membrane into motion, which finally sets the snares into motion. And if you listen to that complete sound, then you get something closer to the real thing. So you can hear the cavity modes now, which really are determinant of the sound quality. Okay, but now let's move to something really simple. So the simplest kind of non-trivial musical system is the string. And here's the glorious wave equation here that we all know, which is an equation describing the time evolution of the displacement of, say, a string in this case. And it's dependent on spatial coordinate and also on time. And there are really just two parameters that define the string. There's the speed, the wave speed, and the length of it, the two physical parameters, and from which you can derive one perceptual parameter, so a fundamental frequency, which in this case is the same as the pitch. And this is, in fact, the heart of the digital waveguide. And like if you listen to it, it sounds like horrible, right? It doesn't sound anything like a string. So that means that there's a lot left to do actually to build this into a real kind of string model. So, you know, the first thing you do is to add a stiffness term. And this means adding another term to the differential equation and adding a new parameter, which we'll just call it here the stiffness. And here, like a lot of things happen, like first of all, wave propagation changes a bit. So you start to see this dispersion as the pulse progresses. And the pitch and the timbre both change. So here's the case where we have no stiffness again, a bit of stiffness, and then finally something more bar-like. So we have both pitch and timbre kind of changing together there. But these are still static tones. So like in order to introduce some decay, we need to introduce a loss term. So here's yet another term we can add to this. And this emulates frequency independent loss. And here's the kind of sound you get out. So it's still really not very realistic, but at least it has the proper tail on it. But actually, like in general, loss increases with frequency. So you'd expect all the high frequency components to die out more quickly. And there's another term to deal with this. And here you're kind of at the, I don't know, minimum kind of passable quality string sound. And I'll come back to something better in a second. But before I get to that, let me talk a little bit about linear and nonlinear systems. So the system we just looked at is linear. And in this case, I guess there's like a relatively simple mapping from system parameters to pitch and to timbre. I mean, relatively simple. And like if you look at other types of instruments like bowed string and wind instruments, these are like kind of harder to examine this way because they're fundamentally nonlinear. So there's no real linear regime. Like bowed strings and wind instruments don't make sound like unless they're driven like by a nonlinear excitation mechanism. But there are other cases where you can get sort of a smooth timbral transition from the linear to the nonlinear regimes, particularly in the case of percussion. And that's the case I wanted to look at here briefly. So a really great example, like illustrating pretty much everything you'd ever want to know about nonlinearities in musical instruments, is the case of a driven metal plate. So imagine a flat, thin piece of metal. So in this case, it's say, a piece of steel, about a millimeter thick, 1 meter by 2 meters in dimensions, and then driving it somewhere on its surface with a sinusoid at a given frequency, and then taking readout from somewhere else on the plate. And what I've got here is a spectrogram showing the time evolution of the readout over as you increase the amplitude of the excitation. So what you see at the beginning of the spectrogram is that under low amplitude excitation conditions, the whole plate kind of settles into the frequency of vibration of the excitation. And then you see harmonics appearing. So you see harmonic distortion. So exactly the kind of things you see in like guitar amplifier or something. But then there's a kind of threshold amplitude where the harmonics start to bifurcate. And very quickly you end up in sometimes what's called the turbulent regime. So now that I've showed you the spectrogram for this sound, let me just play it. So this is synthetic as well. So that noise you hear at the very end, that's exactly the noise that you hear when you hit a cymbal or a gong. So here's a gong-like sound. Okay, but now, backing up now, back to the case of the string, you can develop a very simple model of nonlinear string vibration, but by just adding one additional term and adding one additional parameter to the model. And you actually get a dramatic effect. And I'll just play you, the difference between what you would get from a linear model. And the nonlinear model. So, there's really like a huge amount of stuff going on just with this one term. So first of all, you hear changes in pitch and pitch glides, but you also hear all this kind of like interesting noise happening there too. So, if I were going to go and change fields and get into, thinking about timbre and psychoacoustics, I mean, this is an equation I would probably look at pretty carefully because first of all, it's simple. Like there's just a few parameters here. But it's also like giving you a wide range of behavior. And it would be interesting to try to like pick this apart at some point. Okay, and finally, let me just come back to that prepared piano. So here's a great quote from an oldie from John Cage. So with just one musician, you could really do an unlimited number of things on the inside of the piano if you have at your disposal an exploded keyboard. And this is absolutely true. So if you go back to the simple string model and just introduce like one small rattling thing. So this is characterized by just a couple more parameters like mass and where it is on the string. I mean, the range of timbres just kind of explodes on you. So I'll just play the sound you get in this case. Like there's really a lot of action there. In particular, there's a lot of like sort of sub-audio rate stuff happening there too. And this is actually the basis for the plugin that I showed. So this is one string among the 25 that are running on the plugin. Okay, so I'm at the very end now of the talk, and the one thing I wanted to do is just take you through a piece that we worked on with a musician from Ireland named Gordon Delap. And this was the first piece we did back in 2013 using our GPU physical modeling synthesis system. And it was really a lot of work, actually, because at the time, like control was very difficult. Gordon had to go like type a lot of numbers into text files and stuff like that to get it to work. It took about 5 months of work over 6 visits. Like a lot of it happened actually like towards the end of the year. So towards November 2013, this is what Edinburgh looks like. And in winter if you've ever been there, but it gets pretty spooky. And that, I think the spookiness of the time frame kind of influenced the character of the piece, which was actually a meditation on death and the nuclear holocaust. So it was a pretty it's a great piece, but it's on a grim topic, you know. So one thing that like we decided to do early on was to try to be really systematic about exploring these new tools, because this is the first time we tried it. And by systematic, I mean systematic in terms of exploring the timbre of what was available. So it's a 3-part piece. I'm not going to play the whole thing. These are short excerpts here of about a minute each. But they illustrate this kind of progression through like learning how the instrument worked. And so the first part is actually very simple. And it was just based purely on plate vibration. So like in keeping with the kind of nuclear theme of the piece, Gordon asked that we make all the plates out of uranium. So I guess this is more psychological for him than anything, but we're able to do it. Like you just go track down, you know, Young's modulus and the density for uranium, and you can immediately get a uranium plate. So for the next part, we introduced horn instruments into it. So I should add, this was a 16-channel piece, and like this next part was kind of designed to be almost like a chorus. So if you stood in the middle of a ring of 16, like you would hear horns like coming from each loudspeaker, almost as though there was a person there playing it. So. I remember like Gordon spending a lot of time trying to get the brass instruments to kind of warble, to get that warbling timbre that we managed to get finally, but it was difficult. And then, you know, by this point in the piece, like Gordon was like getting a little bit fed up, I think, of using just synthesis. And he said, do you think I could use just one sample? And we said, yeah, okay. So he went and recorded himself whispering something. But we took the whisper and we fed it through like a big network of plates. So you may be able to hear the like the sample in here, but you may not. And this one also includes a bass drum model as well. So I've tried to go like pretty quickly here today because I know people want to get to their drinks and stuff. But if you do want to learn any more about the stuff we did during NES and also later, just go to the website. There's like papers and stuff and all the music we did. We've done stereo reductions of them all, and they're up on YouTube too. So have a listen. And that's it, actually. Thanks, everybody.
Thanks, Stefan. That was an amazing talk. Actually makes me consider abandon psychoacoustics altogether and just work on differential equations. If I can simulate uranium plates, then.
No, don't do it, man.
So I invite everybody to hand in their questions or indicate their interest for questions. But before people do that, I take the privilege to perhaps ask the first question. So you've talked, or you've given such a great impression of how the details of the physical simulation contribute to our perception of naturalness, right? Mm-hmm. My question is, what do you think, to which extent does our experience with certain physical systems also contribute to perception of naturalness? So, for example, with the uranium plate, most people probably haven't heard uranium plates so far. Hopefully they won't. So to which extent does our experience determine whether we perceive something as natural?
Well, I don't know, actually. That's a good question. It was really important to the composer that it be made of uranium. So I, like as it turns out, like that case is an interesting one because for the model we had, you could have just gone and changed the dimensions a bit for a steel plate, and it would sound the same as a uranium one. And he knew that, but he really insisted on that. So I don't know. I mean, I could almost ask you, like, if it changed the way you heard it because you were thinking about uranium, you know? It actually does change it for me a little bit, but that's wow, that's getting into something quite, like for me, pretty psychological, actually. I don't know, but it's real, whatever it is. I don't know if I can answer any better than that.
Okay. Do we have any questions from the audience?
Oh, I see Sophia.
I don't see any raised hands so far.
I see Sophia Dahl, actually.
Sophia.
Hey, Sophia.
Sorry. Hi. Thank you for the great talk, Stefan.
Oh, thanks, man.
But I wasn't able to raise the hand, so I just had to jump in anyway. So about the naturalness, I find this an interesting topic also, and it's as I understand, it's something that comes also in human-computer interaction in other fields. This natural interaction and what is that, and the definition of natural. And I'm thinking that maybe it's not only about the sound quality as such, but also rather about the responsiveness or how you think about what happens in the sound, like the richness of it, but also the gestural components, so to speak.
Yeah. I mean, the gestural part is really not my expertise, but I learned kind of how important that is through the course of the project. Because, you know, for us, a gesture it's a breakpoint function that you put into a piece of code. And that's as far as I went with it. So other musicians have designed their own ways to interact with this stuff because, you know, using the breakpoint function is the kind of like the common means of communicating with the algorithm. But
yes, but to elaborate that, I think the gestural part, I mean that you hear something, even if it's just one note, or in that evolution of that note, you hear something about the or at least what you imagine it to be with the energy infusion into the instrument, if you get that one. So it's not so much, not necessarily also about transitions between notes, even though you've included that now, but even within the note, because it has something of the richness. At least
yeah, well, it gets tough to even define a note anymore. Like when you get into some of these things. So I don't know, like if you like pluck a guitar note, but there's a lot of bouncing off the frets or something. Like it could sound like several notes. I don't know. Like you lose the notion of a note even. So yeah, I don't know.
Okay, but
I wish I could say more, but
yeah, but that's what I was thinking about. Thank you.
okay.
So we have David.
Hi,
Hello.
David.
Hi, thanks very much for the talk. Very
Hey,
interesting.
thanks.
This is perhaps a naive question, but if you're thinking about just deriving a simple vanilla wave equation, one way conceptually to get there would be to think about, say, linking together harmonic oscillators and taking a continuum limit. Is there some sort of finite dimensional analog for the more complicated sort of string equation? And are there certain nonlinearities that would be characteristic of that?
Yeah. Okay. So, yeah, like, so if you go just to the basic wave equation, you can do that, right? You can view that as a string of masses stuck together and joined by springs. Like it gets harder and harder to do that actually as you get into like other types of systems, like something like a plate, for example. That's a lot harder actually to make that analogy, because you're not just holding on to masses. You have to think about angles and things too. So you could do it, I think, but I think what would happen eventually is you'd arrive at the same thing that like we got initially. So that's been my experience. Like I've tried that too, just to understand that way of doing things, because there's a whole other system called Cordis Anima, which came out in France in the 80s, which is based on that. So just mass and spring networks.
Right. I think I've seen that.
And I was always interested to know like if that's entirely equivalent to what we're doing. But I'm not totally sure. I don't know. Actually.
Okay. All right. Well, thank you.
There's a link for sure.
Next question goes to Jean van der Weert.
Yes. Hi. Wonderful talk. Thank you. You put that John Cage quote at the end, and I wanted to build off that. Just my question. You talk about this electronic music and the liveness of it. I was thinking more of it in a theoretical sense, so you don't have to have an answer. But the act of seeing electronic music being created. John Cage would make his electronic music in public, so people could see it, even though it was electronic. So it wasn't real live music, but it was. And so I wonder what your opinion of this. The act of seeing electronic music being created. Does that still technically count as live or real music, even though it could possibly be duplicated and replayed after the concert? So it's not a singular experience.
Yeah, I think live we haven't, like we're just getting into that right now, because like all the stuff we did for Nest was offline. So that everything you heard was generated like out of real time, and then people put together a piece from that. Now, right. We're getting to the stage where some of the simpler stuff we can move over to real time, like the plugin I showed. And that thing is really weird. Like I don't know if people are going to be able to learn how to play that thing, or if it'll make sense even, Right. But it could be interesting, like right. Like I don't know.
Which is what prompted that question was just thinking about John Cage, because all his music would be able to be played again.
Oh, I see what you mean. Yeah.
So in a way, it's not actually live music. It's because the experience can be duplicated. So it's not like it's just one singular experience. So yeah. Just a thought.
I hadn't thought of that actually. You mean like actually trying to do versions of John Cage pieces, like the prepared piano
right.
stuff? Cool.
Exactly.
Good idea.
Yeah, well, thank you.
All right.
Thanks, John. So next question comes from James Beauchamp, asking regarding the type of software you're using and whether you have tried.
What software is being used for the graphics?
Graphics, that's all MATLAB, actually. Yeah.
Oh, yeah, but it's really cool.
Yeah.
You did a good job with it.
Yeah, thanks, man. Yeah, keep MATLAB. Don't go to Python. Sorry, I shouldn't say that.
They took away the cheap MATLAB on campus here.
Yeah.
Have you ever tried?
I'm fighting for MATLAB because of the graphics. Like that's.
Have you tried expressive synthesis of instruments, classical instruments? That was one thing that came to my mind.
Yeah, like do you mean like orchestral instruments, standard ones?
Yeah.
Yeah, like like we kind of have a sort of a split in the group, actually, not an acrimonious split, but there's one guy that I work with named Michele Ducheschi, and he's the guy that looks at emulations of real instruments. So he's doing, the double bass and the cello and that stuff. And I'm kind of the guy that does the more weird stuff, the stuff for, avant-garde musicians and stuff. So yeah, we do both. I mean, principles are the same.
Okay.
Yeah.
And another thing that occurred to me is that with the brass, you have nonlinear propagation.
I don't in that model. I mean, we do have that model running. In that one you heard, the only nonlinearities in lips. But we could have the shockwave stuff going too. Yeah.
Yeah.
So yeah.
I think Rodet did some of that.
Yeah, Rodet and Masalam, yeah, back in 1999, yeah.
Yeah.
So,
okay,
next question
thanks a lot.
goes to Yannis.
oh, I can't hear you.
Yes, hi, sorry,
No,
sorry, I had a mute problem. I'm not really a timbre expert, I'm a pianist and music theorist. I'm now undergoing this shocking introduction to the field. I would like to ask you, Luciano Berio, I think, was the one who said that for a for a sound to be musically viable, it needs to consist of at least 1,000 sine waves. That was voiced a few decades ago. I would like to ask you on a macroscopic level whether you think that this should be revised in 2020 as a view.
Wow, that's a good question. Like 1,000 sine waves, huh? Like that's more than we have in some cases,
Yeah.
It sounds like a lot, actually.
Yeah.
Like as a basic criterion for viability, that sounds like a lot, but it depends what he means, though. Does he mean like sine waves, or does he mean like, I don't know, degrees of freedom or something? Or is that what he said, sine waves?
I think he did mean, strictly speaking, sine waves, because it was in the context of the 4X synthesizer.
Oh, okay, I see. Right.
Yeah, I think so. Yeah, I'm sorry, I don't have the actual quote to cite, but I'm pretty sure that's what he meant.
It sounds like a lot, actually, to me. I mean, yeah. Okay.
So thanks, Yannis. I think we try to take a couple of more questions. The next one comes from Harris.
Hey, Harris.
Hey, Stefan. Great to see you. Man? Yeah, good. Thanks for that was a great talk. It even reminded me when I started at McGill, one of the coursework that I did was using your prepared piano max patch. That's like a very old work.
Oh, we don't talk about that anymore. Like that was okay. Yeah, that's old stuff.
Yeah, it was kind of a flashback. So I just wanted to say, so in terms coming from timbre perception, and in timbre we have kind of two, let's say, viewpoints. One is timbre as the quality of a sound, right? So this is a bright sound or a dark sound or a sharp sound and so on. A nice sound, a bad sound, whatever. And then there is timbre as a vehicle for identifying the source of a sound or the cause of a sound. Mm-hmm. And in that second perspective is where there's a lot of discussion and let's say a holy grail in timbre research to understand the invariants. Like there are certain invariants that make us always understand that this is a sound where something rubs something, or this is a sound where something hits something.
Do you mean also like that if there's reverberation on something, you would not consider that to be part of the sound then, or part of the timbre, right?
Well, that's interesting because you said earlier that seeing the earlier keynote make you realize that maybe reverberation is not part of what we would consider timbre, but of course, eventually timbre can have a lot of definitions and you can operationalize based on your research question. So for example, reverberation could be an important aspect of, when you knock on something and whether you can understand whether this is an empty object or a solid object. So there, this kind of idea of hollowness or not. So basically, my question is, you know, how can we use the physical modeling field to perhaps better understand invariants in sound perception?
Well, I mean, actually preparing this talk, I don't know if this is going to quite answer your question actually, but like it made me realize, especially for that string model with the nonlinearity in it, like clearly they're just a few numbers that describe that thing. And yet like somehow it's producing this wide range of sounds. So there must be some way to kind of like compress that down actually, or to like to, I don't know, like try to quantify what it is that nonlinearity is doing, even though it sounds like it's doing a lot, it's not. It's doing one thing, and I'm not sure what that is actually. So that, I mean, the invariance, I guess, would have to be the numbers in the differential equation, right? For, I mean, that seems like it should be the simplest way to describe them. But and yet it doesn't seem to be the case. So like most interesting systems are nonlinear, and you get this wide range of stuff happening, but it seems like it should be described by a larger dimensional space, but it's not. So that's mysterious. That's not answering your question, I don't think, but that's.
It doesn't necessarily, I'm not looking for, you know, an answer, but I think it's more of looking at, you know, what we can learn across the two fields, let's say, if we consider them, you know, separate fields.
Yeah, lost. I mean.
Okay, so before we close, we have one more question, and that is, do you compare the sounds synthesized using physical modeling and those generated by AI? Do you see any advantage ciphering?
I don't know. I think like like all the machine learning stuff I've seen, that's going to be really good for the systems that we can't really deal with physical models. Like some things are too complicated. So particularly like environmental sounds or something, like trying to do a physical model of that is just like impossible, right? So at the moment people use like procedural audio or something for that instead. But like that is where it's going to be really useful, because, you know, we can do simple, very basic systems with physical modeling, and like anything more complicated, just forget it, you know. It's just, so that's where it's going to work, I'd say. And speech, as far as I know, like machine learning, like beats it hands down, right? I've never heard a good physical modeling speech system. So, but yeah.
Okay, I think we're all done with questions. Thanks once again, Stefan. There was an
Okay, thanks very much. Cool.
And this closes the scientific component of the talk, and I will leave it to Asteris to explain how we go on from here.
So thank you, Stefan, from my side, and I'd like to thank all the participants and the presenters that contributed to today's